Welcome friends. In the introductory lecture on fuzzy control, we studied about the basics of fuzzy logic, how the crisp sets and fuzzy sets are related. In this sequence, today we are going to learn about the four special membership functions, the graphical representation of the membership functions for fuzzy control, and the expressions of the membership functions in detail. So let us start with the recapitulation of the topic we introduced in the first lecture, that is the fuzzy set. If we can recall the example of the expensive cars, we can say that the fuzzy set of expensive car can be represented as f equal to the fuzzy set f equal to 1 divided by Ferrari plus 1 divided by Rolls-Royce plus 0.8 divided by Mercedes plus 0.7 divided by BMW plus 0.4 divided by Buick. So the same set can be represented as a summation of the different elements of the inverse of discourse, which is a discrete set in this example. So along with the element, we mention the membership function value for that specific element in the fuzzy set. So we can generalize it in the form of function f equal to summation of the all such tuples of the fuzzy set. So starting from I equals to 1 up to n elements of the inverse of discourse, we convert into the tuple like this. So in case we have a continuous set, that is the set of infinite number of elements, like for example we take the example of elements starting from 0 up to the integer 6 with all the real numbers in between. So such a set of elements will be a continuous set, that is a set of uncountable number of elements. So for that, the fuzzy set can be defined as integral over the inverse of discourse u, that is capital U, then mu subscript capital F as a function of an element small u of the capital U divided by small u. So in this way we can represent the fuzzy set both for the case of discrete capital U and for continuous capital U. So if we go little further, the membership functions play a vital role in the case of fuzzy set that we are going to learn in this course. So we can take an example of old people in a given territory from the universe of discourse of their ages ranging from 0 to 120 years. So in this case, naturally the age of higher side will be considered as the old people. So we can define a membership function mu old as a function of an element u. So this is a continuous set. This is a continuous set of u. So now the membership function can be categorized as per the age. So we take examples of 0 is less than equal to u is less than equal to 60 years. We consider that these are not the old people. So then the set of people who are not young but still not old. So for that, 60 is less than U is less than 80, and then the category of old people who will come within the range of 80 less than equal to U less than equal to 120 years. So now the first category is not at all old, so we consider the membership is 0. Second category, it will be a linear change, so we can take U minus 60. So this is basically from 60 to 80, so U minus 60 gradually from 60 it will start from 0 to upper side, divided by, this is 80 minus 60. So when the age is 80, then this term will become 1, otherwise this is 1. So now we can define the membership function as a function of the independent variable small u. So further we will learn how in this way, with the help of membership functions, we can categorize a given range of values with certain membership associations in different groups. So we shall start with the example of the temperature range, which has to be sensed by an air conditioner. So we shall define a temperature range over which it can be very hot or very cold or moderate and comfortable in between. So how do we categorize for designing a fuzzy system like a fuzzy control for air conditioner? How we can define the temperature range? So let us start with that. So first I will start for, let us take the case of temperature range from say minus 20 degree. We say U is a set of temperature range from minus 20 degree to 60. This is the temperature range. So I am drawing a curve. So here this is, in our consideration, this is a set of different temperatures starting from minus 20 to 60, and all temperature values in between will be considered. So we can take it continuous set, because in case of temperature, like the case of age of people in a given territory, we cannot make it discrete because there can be people in between two given values. So similarly in the temperature, there can be a temperature in between two given values. However, for storage in the computer, you have to discretize the data at certain point of time. So if the discrete values are so close, so we can consider them continuous. Let us start by drawing the curve one by one. Curve. So we have the first curve. Here we are defining the temperature in this direction, and we are starting from minus 20. So this is minus 20, then minus 10, then 0. So I am normalizing the value of the membership function, because normalizing means you can have a weightage for each of the temperature to any value. It can be 0.1, it can be 50, 100, 1000, anything, but it is convenient to treat it as a range of membership between 0 and 1. So if we take from 0 and 1, it will be easy to analyze. So without any loss of generosity, we normalize the membership function to 1. So initially I consider that it is very cold, so beyond minus 20, maybe minus 30, minus 40, it was coming constant, and after minus 10 it starts falling down, So after -10 it starts falling down, and nearly 0 it settles. So here in this case I can consider that this is the curve where membership function can be defined as very cold, and when we'll go for the fuzzy representation, we will say this is cold and low CL. So similarly we can define the next range from -10 to +10 degrees Celsius. So we can, how do we define it? So we can define it like this. So if this is the curve, so we are going from -10 to +10 in temperature. You can take any unit for your convenience. You can take maybe degrees Celsius. This is the value of mu on y-axis. This is 1.0, this is 0.0. Then if I go little further, and this membership function I can define as cold, because -10 to +10 can be considered as cold temperature. So further I go and I increase the temperature range from 0 to 20 degrees Celsius. So let me draw the normalized value for membership function. Then I change the value of the membership function over temperature. So in between, this is 10 degrees Celsius, this is 0, and this is 20. So here it is temperature like this. So here I can define this as membership function is cool, because you can say that this is quite comfortable, if not 100% comfortable. That is the room temperature of 25 degrees Celsius. So let us go a little ahead. So here we can say that this cold temperature can be cold medium. I can say this is cold medium, and this is cold small, very less. So next I go for the temperature range of 5 degrees Celsius to 30 degrees Celsius. So maybe I can define mu 0.0, and now the range can be redefined in such a way that 5, then 15, then we can have 20. So we can have here 20, then 30, then I have 30 over here. So this is temperature. So how it is changing, from 15 to 20 we'll have a comfort zone of flatness. So we can draw like this. Like this. So this is the range of flatness. So I can define it as mu comfort. So in fuzzy I can abbreviate this nomenclature as CO. Let us go a little ahead for higher temperature range. We can define the temperature range between 20 degrees Celsius to 40 degrees Celsius. So this is your mu. I am normalizing it to 1.0, starting from 0.0, then like this. So there is temperature in between. This is 30, this is 20, this is 40. So now we are having little warm. So little warm means you can say that the membership function can be defined as mu warm, and this is on the hot but small. So here it is temperature. Go a little ahead, so we can draw the temperature in the range of 30 to 50 degrees Celsius. So we normalize the membership. This is 1.0, this is membership function 0.0. Then I am ranging from 30 to 50 degrees Celsius. Again, this is a curve with a given peak. So here I can define as 30, 40, 50 over here, and this is temperature. So for this you can have the membership function defined as mu hot. So naturally the temperature is hot medium temperature. For that the membership function is mu hot, and further we are going to the higher side of the temperature, that is quite uncomfortable temperature range. So we can define it like this. So we have the membership function mu 1.0, 0.0. Then we have membership function value like this. So this is from starting from 40, you have a value 50, then 60, like that. So this is the temperature. Here I can define it as mu, membership is very hot. So this can be compared to hot large. So once we have drawn the curves, we can now see how in fuzzy logic we transform these curves into the linear graphs of fuzzy logic. So let us draw the fuzzy graphs. So we can draw it like in fuzzy. So we have linear, so how we can draw it? Corresponding linear plot. So we have the membership function as we have defined earlier. So mu is the membership function, 1.0 is the normalized value starting from 0.0. So here is the temperature, then we'll go straight like this, then the fall in the temperature will be a straight curve like this, then we'll go straight again. So this is your -20, -10 and 0. How we can plot it? So this is your exactly cold but large cold value. So let us draw the fuzzy plot for the second one. So this is your membership function on y-axis. So mu, this is 1.0. So once you go for it, we can see that this shape is actually a triangular shape. So we have a triangular shape. We define the membership function very beautifully as capital lambda for this. So let us first draw the fuzzy, then we will go for the specific membership function. So this is from -10, 0 to 10. Here your temperature is growing, and this is cold medium. So let us go a little ahead. For the temperature range of 0 to 20 degrees Celsius, again we will have a triangular plot for this. So we have the normalized value of membership, that is the maximum value of membership function up to normalization is 1.0 starting from 0.0. So we will again have a triangular plot for this. So this is 0, in between this is 10, and I should draw it more precisely so that there is no ambiguity. It's 10, this is 0, and this is 20. So here you have the cold, but small cold. So we define the temperature axis like this. Let us go a little ahead. So now we are having a flat zone over the period of 15 degrees Celsius to 20 degrees Celsius. So let us draw it like this. This is the value of mu, this is 1.0. So this is your, let us draw it as 5, then 5 plus 10 is 15, 5 plus 10 is 15, then 15 plus 5 is 20, then 20 plus 10 is your 30 like this. You can draw. So for convenience I draw the vertical lines so that there is no ambiguity as such in drawing, and accordingly we can draw the plot, meet the lines like this. You can meet the lines. So you see that this has the trapezoidal shape with comfort zone. So I mentioned here COF for comfort, and later we will see how beautifully this shape is defined in fuzzy logic. So let us go a little ahead. Then again we have a curve but with a sharp tip, so naturally this shape belongs to the triangle. So this is the value, 0.0, and here the temperature varies from 20 degrees Celsius to 40 degrees Celsius. So let us draw it like this. This is in between 20 degree, 30 degree, 40 degree. This is the temperature. This is the temperature. So the next plot, again we can find that this is small, and next curve will be again a triangle. So let us see how we can plot it. This is 1.0 mu. So you draw a triangle over here. This is the temperature range from 30 degrees Celsius to 50 degrees Celsius. 50 degrees Celsius. Here it is temperature hot and medium. So we have the temperature axis along the x-axis. Let us go a little ahead. Then we can draw the plot for high temperature range, that is a large value of heat. So again we have to do it carefully. So we have the normalized value from 0.0 to 1.0. Here as we see that we have a large flat approximation. So accordingly we can draw the graph like this, straight lines and a straight flat line. So we start from 40 degree Celsius, then 50 degree Celsius, then further 60, 70, 80, like that we can go. So this is the temperature axis. Now if you see the plot many times in the book, you will see the combination of the plots. So let me draw the curve first. So we have gone from the range of minus 20 degrees Celsius to 60 degrees Celsius. You start from the range of minus 20, then minus 10, then 0, then 10, in between there is 5, then 20, in between there is 15, then 30, then 40, then 50, then 60 and beyond. So this is the temperature axis, and we need to plot the membership functions together on the same plot so that we can understand the effect of the combination of all these membership functions, how we can visualize them. So let us start with the first one. That is, the first one is your curve. This curve is from negative temperature, very low, then beyond minus 10 degrees Celsius it starts falling. So we have 0. So beyond minus 10 degrees Celsius starts falling like this up to 0. This is 0. So for this we can very well write the value of mu as well as what is the fuzzy equivalent. So I'm not writing just for because it will become very complicated in observation. This is first just for your understanding that how it will be merged. Then from minus 10 up to 10 degrees Celsius we have a curve. So from minus 10 to 10 degrees Celsius we'll have a curve like this. Then if you write like this, so cold medium, then from 0 to 20 we have cold small. So we have 0 to 20 we have a cold small. Then from 5 to 30 we have a combination of different shapes. So 5 to 15 it will peak. So 5 to 15 it will peak, then after 5 degrees Celsius it will again fall down up to 30 like this. So here you have the comfort zone basically. So further if we go, then you will see that from 20 to 40 there is again a curve like this, 20 to 40 degrees Celsius, sorry. So there will peak at 30. So we go like this, 20, then peak at 30, then this will go to 40. So this is your small hot range. Then you go for 30 to 50. So when you go for 30 to 50 we'll have a peak at 40. So we'll have a peak at 40, then we can write as hot medium, and then from 40 we are left with very hot. So we can take it as like this, and this is the region of very hot. So we can say it's a hot large, right? So for the same plot, if we want to draw an equivalent fuzzy representation which is exactly linear, so here again the same temperature range we should draw, minus 20, minus 10, then 0, 0, then your 10, in between there is 5, then 20, in between there is 15, then 30, then your 40, then your 50, then your 60, like that. So once we start, we see that we have the point of normalized value of the membership function, and we have the starting point, so 0.0 to 1.0. so we see that the first range is from negative very low, then it will start changing from 10 minus 10. So from minus 10 to 0 it will come like this, which is coming from minus temperature with a very low value, so like this. So this is your very cold region. Then we'll have from minus 10 to 10, so we can have the vertical lines for reference. So we can have minus 10 to 10. This is a triangle of straight lines. These are all straight lines. So this is your cold medium. Then you will have from 0 to 20. So 0 to 20 I can draw like this, then this. So this is your cold small, and then we have from 5 to 30. So from 5 to 15 we go to the peak, so like this. From 5 to 15 you can go to the peak like this, then flat for 5 degrees Celsius, then we will come to 30 like this. So this is the comfort zone, so I give the nomenclature CO. Then from 20 to 40, so we can draw it from 20 with the peak at 30, then 40. So this is your hot but small hot. Then further we go for 30 to 50, so we go for 30. From 30 to 50, then this is medium hot medium. Then the last one will go from 40 to 50, then it will have a flat configuration for high temperature. So this we can nomenclature be given as hot large. So that is how you can transform a curve of the membership functions for a given range of values of the universe of discourse. It can be discrete, it can be continuous. I have taken the example of continuous change of the universe of discourse and its elements, and the corresponding linear plot for the fuzzy representation. So how we can actually in mathematics represent all these different shapes? Let us see. So start with the first shape. We will have the 4 shapes. Actually this is the shapes are the most common membership functions. So membership functions, which are basically the 4 most popular. I am writing capital L, then capital lambda, then capital pi, then capital gamma. So we start with the capital L because of the shape we see on the left. This is of capital L. So for that we define the membership function, the example of which we have seen little early, but now we are going to draw the value of the membership function capital L. Let us see how we can draw it. So we have the function capital L, which is mapped from function capital L, which is mapped from the universe of discourse to the membership value normalized in the range of 0 to 1. So here the function L can be defined as a function of 3 parameters. First is your element of capital U, then 2 other parameters are alpha and beta. How we can utilize these values? Just let us have a look on this. We take the range starting from U less than alpha. So that is basically the value from here in the plot. We can see alpha, and the point where the linear curve falls to 0 is beta. So then we can define as the 3 range, that is the u less than alpha. Then we can define alpha is less than equal to u is less than equal to beta, and the third one is u is greater than beta. U is greater than beta. So naturally, for u less than alpha, that is this range in the figure, this range will give you the value 1. Other one is falling linearly between alpha and beta, so we can define it as a function. The higher value is written first, beta minus u divided by beta minus alpha. Beta minus alpha. So you can check it very well. When u is alpha, this is 1. When u is beta, this is 0. So after the value reaches beta, u reaches beta, it becomes 0. So that is how the membership function L can be defined. Similarly, we can define the membership function for this shape. This is the shape of capital lambda. So for capital lambda, we can have 3 parameters other than u, that is the alpha, beta and gamma. So if we are defining the function lambda, function capital lambda mapped from u to the membership function value, it is a continuous set in the range of 0 to 1, the closed interval. Then the capital lambda, I can write capital lambda, this lambda, capital lambda is defined as, because it is a function of u as well as alpha, beta and gamma, so we can define it as, so naturally you have the 4 different ranges. When u is less than alpha, when alpha is less than equal to u is less than equal to beta, when beta is less than equal to u is less than equal to gamma, and when u is greater than gamma. So these 4 ranges should be satisfied. So for this we should have the values 0. Then for the range which we're considering between alpha and beta, so here it is increasing like this, so it will start from 0 and end at 1. The value should start at 0, so end at 1. So accordingly we can define it as u minus alpha divided by second term is beta minus alpha, like this. So when starts at u equal to alpha, it is 0, and finally at u equals to beta, it is 1. So similarly, from beta to gamma, how we should define? We take the higher value first, so the gamma minus u divided by gamma minus beta. You remember that this is always a positive value, however the slope is negative, so accordingly the value should be positive. So the third one is when you are beyond gamma, so your value should be 0. So that is how we can define the membership function capital lambda. So this is again the membership function capital lambda, so which is a function of u, alpha, beta and gamma. Again here in the figure we see that this is a trapezoidal shape. So this is, because of its trapezoidal shape, it got a special name called the capital pi. So here the function we define capital pi mapping from capital U, that is the domain, to the range 0, 1, that is the closed interval. So here capital pi, pi, comma, capital pi you can write like this, which is the function of U, comma, alpha, beta, gamma, delta, alpha, beta, gamma, and delta all small. So here you have the values like alpha, beta, gamma, and delta. So we can understand here that you have the 5 variables in the as argument. So naturally your range should go like this. So we'll go for the range of, this is equal to, in the range of 5 constants should be there. U less than alpha, then alpha less than equal to U less than beta. The constants you have to note carefully. Beta less than equal to U less than equal to gamma, then gamma is less than U, is less than equal to delta, then U is greater than delta. So we should write here, define here, because that is the clause, so we should write for all like this. So here again this will be first value is less than alpha. We can see that in the plot this is 0, the value is 0, so this is throughout 0, so we can write 0 very well for all alpha U less than alpha. Then we have to take the value alpha to beta, it is increasing linearly, so we can write U minus alpha divided by beta minus alpha. So for this it is increasing linearly, then it is a constant between beta and gamma, so we can keep it 1. Then from gamma to delta it is again falling, but value is positive, so accordingly we can write delta minus U divided by delta minus gamma, So this is for the range gamma is less than U is less than equal to delta. Then when U is greater than delta, we can have value 0 over here. So likewise, this way we can define the pi function, that is the pi membership function in the fuzzy set. So from the graphical representation how the functions are correlated, you can understand very well. So this is again your lambda, you have the function lambda, which is again a function of parameters U, alpha, beta and gamma. U, alpha, beta and gamma. Again the next function is lambda, so it is again a function of U, alpha, beta and gamma. So again the next function is interestingly of the shape of capital gamma. So now we will go to define the function capital gamma. So how we can define the function capital gamma? So function capital gamma can map from capital U to the range 0, 1, and so gamma is a function with parameters alpha, beta, and then if gamma is dependent on U, alpha, beta with alpha, beta parameter U as a variable, so these 3 are arguments here. So because of 3 arguments we have the range U less than alpha, then alpha is less than equal to U is less than equal to beta, then U is greater than beta. So for this, the first it is coming from the 0 value in the past, so we keep it 0. Then the second one is a linear increase, so naturally this is alpha and this is beta, so this is U minus alpha divided by beta minus alpha, then the last one is a constant one. So for all these values, these constants, you get the value of the function. So this way you see that we can define a given membership condition for a universe of discourse that can be a continuous set or that can be a discrete set, but upon that we can define some curves, and from that in fuzzy logic we use the linear functions. So we have the linear plots of those membership functions that can together be represented in the way we have seen here, like this, and from this we can define the membership functions, that is the capital L, capital lambda, capital pi and capital gamma. So this much is the dissemination for today, and in the coming lecture we shall go for further details, especially the properties of fuzzy sets. As mentioned in the first lecture, we can refer to the textbook by Rajasekaran and Vijayalakshmi Pai, and there is another book by Driankov, can be referred for learning fuzzy control. If you find this lecture useful, please like the video lecture, and if you have not subscribed the channel, please subscribe it and set the bell icon below the video link next to subscribe, so that you can activate the notification. So whenever a video lecture is uploaded, we can be notified about its upload. If you want to ask any questions or queries, you can send your queries through the email neurofuzzysystemsfaq@gmail.com. However, my students can approach me through WhatsApp and my mobile number. Thank you for your patient listening.